Right, this is the next video for the Year 1 Further Maths Pure. We're looking at 9D. Now we've looked at using the dot product to find the angle between two vectors. The angle between two straight lines uses that technique. So here's a straight line, 741 plus S 223. And 211 plus t 3 minus 8 minus 1. Now, here are two straight lines. In 3D space, it's not true that all straight lines will intersect. If they don't, they're called skew lines. Clearly, if they're parallel, they're not going to intersect, but they can also not be parallel and not intersect. It's not true in 2D. If they're parallel, they intersect. If they're not parallel, if they're parallel, they don't intersect. If they're not parallel in 2D, they do intersect. So if two lines intersect, I can use the dot product to find the angle between them. Now remember that in the equation of a straight line, my position vector just gives me a point on the line. I don't care where the line is. I only care about its direction part if I'm just calculating the angle between two lines. So to work out the angle between these two lines, if they intersect, and we're told in example 18 that they do intersect, to work out the angle between them, I'm just going to use the direction parts. And I'm going to, like I did in the last exercise, use the two definitions of the dot product. So we'll find the scalar product uh, 6 minus 16 minus 3. Let's find their lengths. 2 squared, 2 squared, 3 squared, 9 and 4 is 13, not the 4 is 17. And 3 squared, 8 squared, and 1 squared. 10 plus 64 is 74. So I know that mod A, mod B, cos theta is equal to the dot product. This is now the same as what we did last exercise. So cos theta is minus 13 over root 17, root 74. So theta is 111.50. Now the question wants the acute angle. So of course, if I've got two lines, I've just found the obtuse angle. So to find the acute angle, I just take away from 180. So the acute angle is 68. Oops, 6. Let's try that again. 68.50 degrees to 2dp. So not a lot new there, just remembering that if a straight line is involved, and I'm talking about finding the angle between two straight lines, or a straight line and a plane, and that's what we'll come on to, I just use the direction part. Okay, before we look at example 19, just another concept to think about. So here's my plane. Here's my normal vector. Let's put the plane on some sort of axis. I won't draw the third axis on there. On my plane, I've got the point R, which is the general point. Sorry, that should be capital, shouldn't it? The general point, x, y, z. And of course, its position vector is R. I've also got another point, A, and its position vector, that's an awful straight line, but you get the idea, is A. Now, the vector from A to R, to get from A to R, I go down A and up r. So vector AR is r minus a, or minus a plus r. Now I know, because that's AR is on the plane, I know that my normal vector must be perpendicular to it. That's what the normal vector is. So my normal vector dotted with that AR vector must be equal to 0. Now you might want to pause and rewind and understand why I've done that, but it's true. The normal vector must be perpendicular to the vector between A and R, because that's what the normal vector is. It's perpendicular to all vectors on the plane. Now you don't have to have done the challenge question from the last exercise, but the challenge question was prove that the dot product is distributive. That just means that n dot r minus n dot a equals 0. It means we can expand these brackets with a dot multiplication in the same way as I would with a scalar multiplication, because that's all it is. It's just a multiplication of vectors. So n dot r equals n dot a. And now I prefer to think of it as r dot n equals a dot n. And this is a bonkers result. What it means is, for any point on this plane, the dot product of its position vector with the normal vector is the same. It'll always be the same as the dot product of a general point with a normal vector. It doesn't matter where I pick on the plane, I'll always get the dot product to be the same. And that value uniquely defines this plane. There's only one plane where this will have a particular value. So this is another equation of a plane. The scalar product form of the plane. I'll open up my, you can't see it, but I'll open up my formula booklet. We're not given that form. I don't know who's decided what doesn't go into the formula booklet, but we're not given that form of the plane. So we've got r dot n equals a dot n. That's the same as ax plus by plus cz plus d equals 0. And we're told that d is minus a dot n. Now, of course, ax plus by plus cz is the normal vector dotted with r, because r is xyz. Dot that with my normal vector, abc. A dot n, well, that will be minus d, or plus a dot n. They are actually the same thing. Ax plus by plus cz is r dot n. So the scalar product form and the Cartesian form of my plane are the same thing. Again, something to pause and get your head round. So if I know my normal vector and I know any point on the plane, I can write either form of my equation, because my normal vector will go into there. If I know my point, I know x, y and z. And also if I know my point, I know a dot n. So, example 19. So I've got a point. A is 2, 3, 5. No, sorry, minus 5. N is 3, 1, minus 1. So in scalar product form, r dot n equals a dot n. Well, r is my general point, so r dot 3, 1, minus 1 equals a dot n. So we'll leave the left hand side as it is because r is my general point. 3, 1, minus 1. So 2, 3, 5 dot 3, 1, minus 1 is 6 plus 3 minus 5. 9 minus 5, that's 4. Have I done that correctly? No, I haven't. It's minus 5 times minus 1. So it's plus 5. So it's 14. That's better. So that's much easier. Well, it's not easier. It's just more efficient, I guess. Of course, now I know that a dot n is 14. Remember, we're given that formula. So d is minus 14. So straight away I can just write for the Cartesian, I just use my normal vector. In fact, I just write the dot product on the left hand side. 3x plus y minus z, move my 14 over. That must then equal 0. Straightforward enough, isn't it? If we can get our head round, or even just remember r dot n equals a dot n, this isn't too bad, I don't think. I'll do 20 and 21 and you can pause and rewind as you wish. Now let's go to a new page. Okay, so if I have my plane, now I'm going to just do a quick sketch. I'm just going to look at my plane side on. I'm not trying to draw it in 3D. I'm looking at it from the side. So there's my plane. There's my normal vector, which is perpendicular to the plane. My line must intersect the plane unless it's parallel, because remember the plane is infinitely big and the line is infinitely big. So there's L1. And I want theta. Well, of course, what I can do is I can find the angle between my line and my normal vector and then take it away from 90. And if the question says find the acute angle and I get an obtuse angle, then I just take it away from 180. So find the acute angle between, what have I got? The line, L1, R is 2, 1, minus 5, plus lambda 3, 4, minus 12. Remember, I'm just going to use the direction part and I'm going to dot that with n. And the plane, they've given me in scalar product form, which is fine. 2 minus 1 equals 2. Don't care about the 2. All that does is locate the plane in space, but I don't care where the plane is. So I'm just going to use the direction part and the normal vector. Do the dot product, so 3, 4, minus 12, dot 2, minus 1, 6, minus 8, plus 12, 18 minus 8, that's 10. The modulus 3 squared plus 4 squared plus 12 squared, better do this on my calculator, 144 plus 16 plus 9, oh that's convenient, 13, and 2 squared plus 2 squared plus 1 squared root 5. So mod A, mod B, cos theta equals dot product cos theta 10 over 13 root 5. So theta is let's do inverse cos of that. Actually, it's actually phi that I'm going to find, isn't it? 10 over 13 root 5 is to 9.879. That's the angle between the line and the normal vector. So the angle between the line and the plane is, take that away from 90, .12. Now that's not what they got in the book. Hold on. Oh, look at that. What an idiot I was. I'm going to fix it rather than do this again. Of course it's not root 5, is it? It's root 9, which is 3. So it's going to be 13 times 3. 13 times 3. Try that again. 10 over 39 gives me 75.143. No, yeah, 143. So the angle between the line and the plane is 14.86. Of course it is. What an idiot. Forgive me. Right, I might as well do example 21 while I'm here. Okay, so I've got two planes. I'm going to draw them side on again. Here's one plane. And there's its normal vector. Let's call it N1. Here's another plane. I'm looking at it sideways, don't forget. And there's its normal vector, N2. So you can see that the angle between the planes plus the angle between the normal vectors must add up to 90 degrees. Because of course each of those normal vectors is perpendicular to the plane. So 90 and 90 is 180. What did I say? Adds up to 190. Who knows what I said. Alpha plus theta must add up to 180. So it doesn't really matter whether my normal vectors are defined towards, away, or one in either direction, because if a question wants an acute angle and I find an obtuse angle, well, clearly I can just take it away from 180. You know, that alpha there is actually going to be the same as that alpha there, isn't it? Because they add up to 180. That theta there is going to be the same as that theta there because they add up to 180. So whether I'm finding the acute or obtuse angle between the normal vectors, the acute and obtuse angle between the planes is the same. So for example 21, let's have a look. I've got r dot 4 minus 7 equals 13 and r dot 7 minus 4 equals 6. So I'm just going to find the angle between the normal vectors 4 minus 7 dot 7 minus 4. 28 minus 16 minus 28, so that's minus 16. Let's try and find these lengths properly now. 16 plus 49. Actually, they're both the same. They'll be the same length, won't they? 16 plus 49. Square root is 9. So mod A, mod B. 9 times 9 times cos theta equals minus 16. Clearly I'm going to get a negative value for cos. I'm going to get an obtuse angle, but it doesn't matter. Cos theta is minus 16 over 81. Theta is, here we go, 101.393. Again, the question is asked for the acute angle, so the acute angle between planes is, take that away from 180, 78.61 to 2 dp. Okay, have a go at 9D. Let me know if you need anything. Bye bye.